Okay, let's continue. All right, we finished talking about the physical, mechanical, electronic, magnetic, and performance characteristics of hard drives, and we had a short look at flash memory as a possible contender for a non-volatile storage place in the memory hierarchy. Now we're going to change just a little bit and look at reliability and dependability and availability. Those are three words that have slightly different technical meanings, even though they all sound like something good. We would like our systems to not fail. We would like our systems to be able to work for us and not have downtime. And especially a hard drive, if it fails, we could have critical loss of data. So these are scary things. If you've ever had a hard drive failure, and not been able to recover your data because you didn't have backup, you know that it's very serious. Now imagine that it's not just you, personal, 22-year-old student, it's a company, and the business is lost, okay? And so a lot of people become unemployed, a lot of money gets lost, and there's lawsuits and anger, and the computer engineers are dodging bullets or maybe looking under their cars before they get in. I mean, things can get really touchy when millions of dollars are at stake. People get real angry. So let's look at reliability, availability, and dependability just briefly, and then we'll move into a way to help improve our disk performance and availability at the same time. Okay, dependability, reliability, and availability. Start out with some definitions. Okay, reliability is measured as the mean time, average time to failure, MTTF. You in fact saw that on the slide about both hard drives and flash drives. There was an MTTF number that was quoted. It was over 1 million hours in both cases. Yeah.
Isn't it the correction of the data? I mean, you fetch data from the disk and it may be wrong, so it's not reliable. Is it wrong?
Yeah, I mean, the ability to get good data is defined as reliability. If the disk crashes or the disk doesn't crash but gives bad data, in both cases it's a failure. Yeah. I didn't mean only kind of failure is the disk dies. There could also be mistakes in the data. That's the same thing. It's considered a failure. Your system wasn't reliable. Okay, now when you have a service interruption and you don't have service from your device for whatever reason, then you have to fix it. Fix the data or fix the device. So the mean time or average time to repair it is MTTR. And the availability is the percent of time that the system is up and running. And that's simply mean time to failure divided by mean time to failure plus mean time to repair. So I think you can see that if this is big and this is little, you'll have a very large availability, approaching 100%. But as this gets big and this isn't so big, you could have availability of, 90, 95, 98. That's not very good. 98% availability means out of 100, every 100 days, 2 days, your system's not working. So what are your employees supposed to do on those 2 days? Just drink tea and play games while you pay their salary? Sounds fun, unless you're the boss or the owner or the customer who wants useful work done. Well, we can't. The computer system's down. Have you ever had an answer on the other end of the phone? The system's down. I can't do it for you today. Whether it's a government memo or a person in a business or whatever. Sorry, doesn't work. Computer's not working for us. What happened there? We had a failure of the system. Okay, so here's a formula that actually can help us to determine our availability, and it's a numerical number. So now we can work on making this greater and making this less, okay? So to increase the mean time to failure, you either need to improve the quality of the components so they fail less often, or design the system to be able to continue operating even in the presence of a failure, which would mean there would be a backup or a YEDEC or an extra component. So if I have 2 and 1 fails, I've still got 1 up and running. If I have 3 and 2 fail, I'm still up and running. Did you know that on manned space expeditions, they often have not 2 processors, not 3, not 4, but 5 parallel computers running the same algorithm with voting. Okay, if anybody's the odd ball out, they kick it out. Now there's still 4 up and running. If it has a failure, it says repair yourself and come back in, we'll try you later, but right now you're out. So we're going to compute in parallel and vote to test who's actually getting the same result. Anybody gets a different result, the obvious conclusion is you're wrong. Something's wrong with your software or your hardware. You need to get fixed or get out. All right? So 5 can stand a failure down to 4. 4 can stand a failure down to 2, 3. What happens when we get down to 2? Running them both, and they get different answers. Which one do we trust? Yeah. So 2 means we're at risk of system failure. 3 means we're still up and running. 4. So it can withstand, as you see, multiple failures. But of course, humans' lives are at risk when you send them off to the moon or into space. And so you need to have that level of redundancy. So that's called redundancy. Designing the system to continue operating in the presence of faulty components. You could either avoid faults, that's the first thing, by improving the quality of the construction of the thing, or you can tolerate faults by using redundancy. And that's what we're going to talk about here is actually fault tolerance by having extra components, extra hardware, that will allow us to either correct it or bypass it. And the example I gave of manned space expeditions would be that. We'd have a redundancy of 4 extras along with the original computer in order to be able to make very sure or highly likely that people don't lose their lives. Okay, faults can be transient and they go away, or they can be permanent. If you tell the computer that's giving a wrong result, go run self-test and come back and try again. We'll see if you fixed or not. If you fixed, it's a transient fault. If you're permanently not able to compute that, you've got a permanent fault. And we're not going to make the astronauts repair you, or maybe we will. I don't know. You know, just depends. All right, now, one of the ways to do this with disks is to have redundancy with extra disks. And so RAID stands for Redundant Array of Inexpensive Disks. Redundant Array of Inexpensive Disks. For example, here's 4. These 4 disks are small and inexpensive, and they may have the capacity of 1 big expensive disk. Okay? So the idea is that we're hopefully not spending more money, but we're gaining something in reliability, and in a minute you'll see even performance. The first thing is I can potentially increase my throughput, because if I write to all 4 at once and read from all 4 at once, my bandwidth will be 4 times that of a single disk, won't it? Because I'm doing parallel read and parallel write. So the amount of bytes per second I get with this is factor of n higher. So I get potentially much higher throughput when I have multiple disks. You spread the data over multiple disks. For example, the first byte here, the second byte here, the third byte here, the fourth byte here. Read me those 4 bytes. Boom. It's in 1 disk read time, not 4 disk read times. Okay? You make multiple parallel accesses to several disks at the same time. Now, the problem is we added disks, and so if the failure rate of this one is 1 over 100, then the failure rate of these is now 4 over 100, right? So whatever the failure rate is, you add them up, so you can see that I'm going to have a much greater chance of failure by adding extra components. So I need to do something intelligent here to make these not independent, but backups of each other. So availability can be improved. Now, this made it worse, but now we can make it better by adding redundant disks. Okay? So lost information can be reconstructed because I have extra copies of it. In other words, if I have these and they don't have any shared information, then when this one fails, I've lost information. But if these two had these 2 as copies, then if any disk fails, I've got a backup for it. Okay? So now what I can do is simply make the mean time to repair be small in a few hours, make the mean time to failure be huge in terms of years, and I'll have very, very high reliability. Now let's see how we might do that. Okay, RAID levels. RAIDs are talked to different architectures, and they call them levels. This is level 0. Level 0 has no redundancy, so we don't have any extra reliability, but we do have parallel access. We call it striping, and what we're going to do is we're going to take sector 1, byte 0, byte 1, byte 2, and byte 3, and put them in parallel on the 4 disks. So I'm going to get a performance improvement of 4 on this. The multiple smaller disks, as opposed to just 1 big disk, by spreading the sector over multiple disks, allows me to access multiple blocks in parallel, and I'm going to get a big increase in throughput. This 4-disk system gives a performance 4 times higher than a single disk. And if these are each 1/4 of the size of a single disk, a little bit, the cost might be roughly the same as 1 big disk, assuming that the 4 disks cost the same as 1 big disk. That's really not totally true, because that's 4 motors, 4 cases, 4 fans, 4 drive electronics instead of 1. But the problem is there's no redundancy here. Nothing is copying anything else. So now my failure rate is 4 times higher than it was with a single disk. Okay? So if a disk fails, I lose data. If this one fails, I can't get all of sector 1 because I lost a byte of it that was on this disk, or all of any sector. So what I need to do is add redundancy. This has no redundancy, but it shows the performance improvement by striping. Get it? I stripe the data like a chariot, okay? I distribute the data over the disk. Now, level 1 has redundancy via mirroring, but no striping. So whatever data is here, I make a cloned copy of it over here. I have redundant data. So I doubled the number of disks, but now every disk has a backup. If I get a problem on this disk with data or read electronics or the motor or the platters or whatever, I've got everything that I want right over here. So therefore, I don't lose system availability with one disk failure. In fact, I could withstand as many as 4 disk failures and still have the system running if the 4 disk failures were this one, this one, this one, and this one. On the other hand, as few as 2 disk failures could crash my system if they happen to be the redundant disk on its copy. Okay? So, but at least I can stand 1 disk failure. All right? So if the reliability of 1 disk is x, the chance of double disk failure is x 1 over x squared. So now you can see it becomes very, very, very low probability event. And if this one fails, but this one is still up and running, what I'm going to do is repair, replace, copy over, and now I'm back up and running. So I didn't lose any system availability time, and I'm back up to full reliability in a short time. But if this one fails, and before I get it backed up and a new one in, this one fails, oh, I've had a double failure. That's why you want to have fast repair. And you go to Google, you go to Amazon, you go to these places with thousands and thousands of disks. They want to quickly get the bad one replaced before the one that's its backup might also fail. And the chance of a failure in the next 2 or 3 hours when you have thousands of disks is non-trivial. Okay? So if you're going to have 3 or 4 failures a day, then you want to be sure you're getting the disk repaired within a matter of minutes, certainly not hours. Because if you have your mean time till repair window of hours, you might end up with other failures falling in that window, and they might involve the places where the redundancy happens. Yes?
What if we read different values from sector 3?
Yeah, okay. If we write, we write to them both. If we read, we're just going to read from one, because we're going to assume that they're copies of each other. But yeah, you're right. There's a small chance that when I try to write them both, something happens and they're not perfect copies of each other. But we're going to work as hard as we can to make sure that that doesn't happen. Because then we end up, just like I told you in the astronaut, this says A and this says B. Who's right? So. All right, if one disk fails, here's the key here. If one disk fails, the system just goes to the mirror. So we call it mirroring, like an ayna. Does everybody see that? This is the mirror. Whatever's here is also over here. So this adds reliability, but not performance. And obviously, I can put the two together and have striping with mirroring, and now I get reliability and performance. So with these 8 disks, my performance is 4 times the performance of a single disk. And my reliability is the square of the reliability of a single disk, because now it takes 2 failures, and in fact it has to be a particular 2 failures. If these 2 fail, I'm still good. If these 2 fail, I'm still good. If these 2 fail, I'm still good. If these 2, if these 2, if these 2, the only pair of failures that'll hurt me is that pair, or that pair, or that pair, or that pair. Some double failures will hurt me, but not all double failures. So I actually have very high system reliability with this and high system performance. But the problem is, it doubled the cost. Adding reliability here said I need as many extra disks as I had originally. So that's level 1 plus 0. Level 2 says we can do better than that. We can use less than a full mirror and use what's called memory-style error correcting codes. Memory-style error correcting codes. This uses the very same system that is used in correcting errors in memory. Let's see how that works. Here's my 4 data bits, and this parity check checks 4, 5, 6, and 7. In other words, these 3 and this form a parity word together. So you can see that if I'm using even parity, the value here should be, I'm using even parity, the value here should be 1. Yeah, okay. This checks 2, 3, 6, and 7. So 2, 3, 6, and 7. So that means these and this, if this is even parity, the value should be 0. And this one checks 1, 3, 5, and 7. That's 1. So therefore, 3, 5, and 7, I need to have a 1 here. Okay? All right, so now we understand how to write the value. Obviously, if I have a failure with any of them, I can figure out in reverse what the value needs to be and recover it. So I can tolerate limited disk failure since the disk can be reconstructed, similar to tolerating limited memory failure. If you get a memory error, it can be corrected using an exact same scheme as this. Let's see how that might work. Okay, so those are the values. Now let's see what happens if we get a failure. Okay, so we're going to let that go to 0. All right, now we have an error in one of our disks, but we don't know which one. Let's figure it out. Is this the right parity value for 4, 5, 6, and 7? 0, 0, 0? No. So 4, 5, or 6, or 7 have a problem. Is this the right parity value for 2, 3, 6, or 7? 2, 3, 6, and 7. Is it the right parity value? 0, 1, 0, 0? No, it should be a 1. So that one and that one both tell me something's wrong with 6 or 7. Because they both say 6 or 7. Now this one is going to tell me if it's 6 or if it's 7. If this is the right value, 7's okay and the problem was with 6. If this is the wrong value, 7's got the problem and 6 is okay. So let's check it out. 1, 3, 5, 7. 1, 3, 5, 7. It's got 2 1s. It's even parity. That's okay. So therefore 1, 3, 5, and 7 are okay. Therefore 6 is the one that's got the trouble. So 6 has gone bad on us, and sure enough, 6 has gone bad on us. So now we know which disk. Not only which disk has got the error, we can correct the data. If you know that this is wrong and it's a 0, it therefore should be a 1. So if I take this disk out and I read the values on the other disks, I can figure out what to put on the new disk. So let's say this one died and I lost the whole thing. I can bring in a brand new disk and using these values recover what I need to put on here completely. If the whole disk dies, I lose every member of this disk. The other bits which are stored in parallel on the other disk can help me how to reconstruct it. Any questions about this? Okay. Yeah, it's a little more economical than this. Look, this one here has 4 for 4. This one has 3 for 4. Whoops, going backwards too far. Hello? Come here. Now, how many extra disks do we need here? The answer is approximately the log of the total number of these plus 1. The log of the total number. So in this case, it's 2 plus 1 more. So it's not going to be as many. It's going to grow basically as log, so less than double the cost. All right, I saw some hands up, so I'll take some questions about this method. Yes? Okay. These are called group parities. This parity bit checks 5, 6, and 7 and forms a group. This parity bit checks 3, 6, and 7 and forms a group. And this parity bit checks 3, 5, and 7 and forms a group. And can you see that 3 happens to be in that group and that group? 5 happens to be in that group and that group. 6 happens to be in that group and that group. And 7 happens to be in all the groups. So every one of these is multiple checked. Because I have intersecting sets, I can identify which one went bad. That's the theory behind it.
How the 4 is failed?
How the 4 is failed? How the 4 is failed? What do you mean? 4 didn't fail. This failed. This failed. This failed. Watch the animation again. Look what happened here. I've got a problem there. It went from 1 to 0. Okay, I've got a wrong data here. The question is, which one is wrong? I can tell you right now that's the wrong parity, and that's the wrong parity, and that's the right parity. If these are both the wrong parity, which disks can be bad? 6 or 7. But this is the right parity. So 7's okay. So 6 is the disk in error. That's where I had.
Yeah. 3, 5, 6, 7 our data.
Yeah. Yeah.
And 4 to 1 are
checking bits. Yeah. Right.
What if 4 or 2 is failed?
Then I can. Okay, great. If he's asking the question, what if this fails? Then I'm going to ask you the question, what will happen here? What will happen here? It'll pass. It'll say 4, 5, 6, and 7 are all fine. So 4 is fine, 5, 6, and 7 are all fine. What will happen here? It'll tell me 1, 3, 5, and 7 are fine. So 1 and 3 and 5 and 7 are all fine. So now I've got 4 is fine, 1 is fine, 3 is fine, 5 is fine, 6 is fine, and 7 is fine. And this one's bad. But I already know 3, 6, and 7 are good, so therefore 2 is bad. So therefore I know which one failed. Okay. Any questions? Let's move on. Okay. Now let's move to level 3. Okay, level 3 has got even less redundancy. Do you notice what happened here? Now I've got down to a single extra parity disk. So it's n data plus 1. Not n plus n, not n plus log n, now n plus 1. This is much more economical. I hope everybody can see that. Does it still give us the fast high performance? Sure. We stripe the data across here. 4 parallel reads, 4 parallel writes, or n parallel reads, 8, 16, 1024, whatever you want to do. If you're Google, I'm sure n is very, very large. That's not a big deal for us. We're striping. The key is, how did we get redundancy with less and still cover and get our error, not just detection, but correction. I need to be able to fix my errors, okay? In this case, I have to know which disk has got the problem, and the 1 extra bit will tell me what it needs to change to fix it. If I tell you that there's a problem here, let's say, for example, 1010, and I put a 0 here, that's wrong, because it's odd parity. 1010, if I have a 0 here, somebody's wrong. That one could have failed, 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 that one could have failed. If I know which one failed, I can fix it. You tell me which one failed, I'll change its bit, now it's fine. How will I know which one failed? The answer is I need an independent mechanism, and the independent mechanism is this. Every disk sector is stored with a checksum that tells you if that sector has gone good or bad. Every disk sector on every disk has a checksum that says this is good or it's not any good. So therefore, if I know this one's failed, then I can change it from 1 to 0. So of all the bits in that sector, I check against all the parities, and I find out which ones are bad, and then I'm able to fix them. But I have to know which disk has the failures in the sector. Okay, so let's see how it works here. Because I'm doing a parity to generate this, I also can check it. Do you remember we studied parity, I think, in CS-224? You can generate it, and you can also use the same exclusive ORs to check for parity. You can generate it and add the parity bit. That's when you're writing these. When you're reading these, you check it to make sure that it's okay. So that's easy to do, and it has reduced it by a double mechanism. One mechanism is contained on the disk to say, I've got a problem here locally, and then this tells us exactly which bit needs to change. Okay, so this is called bit interleaved parity. The number of redundant disks is much smaller now. Reads and writes have to access all disks. And you see that when I read anything, I have to read them all. When I write anything, I have to write them all in order to generate the parity. Yeah?
Sums can find the cause of the mistake, then why do we need disk to find the...
Take this out. Now all I know is there's a problem on this disk. I don't know which bit. I don't know how to change it to fix it.
But you said that every sector has...
Yeah. Yeah. Here we go. Sector 28. Here's the check bits. The check bits tell me bad. Great. Fix it for me, please. 512 bytes. Which bits are wrong? All I know is there's a problem in the sector. I don't know which bits are wrong. But now, because I'm doing this literally, the first bit here and the first bit on the next disk, all the first bits are being exclusive ORed together to form that bit. And the second bit here and the second bit here and the second bit here all being exclusive ORed. Then I can get it down to exactly which bit or bits need to be repaired. Got it? Yeah. So that's it. I need to know which disk it was, and then I can get down with this to the bit level and fix all the bits. That means that if this disk dies completely, I can bring a brand new disk from Seagate, stick it in, use this information, and fix every single bit. Every single bit. Recreate a dead disk. Okay, that's the key here. Recreating a dead disk, because disks die. If you run a factory full of disks and they're running 24/7 and you have hundreds, in a week you'll have some failures. In a year you'll have a lot of failures. If you have thousands, you'll have so many failures you need to have people running in there to fix and change the disks. Okay? Who has thousands of disks? I'm sure there's examples right here in Turkey. Big systems, big government systems, big computer systems need lots and lots and lots of disks. Hundreds, Easy. Thousands maybe. Get over, I mean, thousands, you know. It's not a big deal. And it's better, as you've seen here, to have a lot of little disks than it is to have 1 or 2 or 3 big disks. Why is that? Because if you have a lot, you get the huge bandwidth of parallel access. If you shrink it down and don't, if I have 3, I can only write 3 at once. If I have 30, I can write 30 at once. Got it? So storage capacity equal, it's better to have more disks, as long as you take care of the reliability issues. And, okay, so we're trading off here, aren't we? Everybody can see this, trading off performance with failure rate and reliability. Okay, yeah. Yeah, sure.
Let's say you are carrying these data with buses, and you had a failure in the bus, and the correction is set to good.
Well, I'm going to be real honest with you. Whenever I'm going to send data, I'm going to send parity, which can do error checking and correcting. Not just one parity. I'm going to send. So therefore, when I send this, I write these. At the other end, when I get it, I check. I mean, if reliability matters to me, then failures in memory, failures on buses, failures on disks, I'm all over them. I'm spending my money and my time in order to assure reliability. If you don't care, you say, it's okay. What's 1 bit? You know? What's 1 bit? Turkey's population just went from 70 million to 7,000 because a bit changed. You know, what's 1 bit? Your bank account just went from positive to negative, and they're sending you notices the lawyer is going to send you to court because the credit card is default. You say, what? No. You know, what's 1 bit? Well, here's the best example. The rocket's going this way. Now it's going this way. Just change 1 bit. You know, does it matter? Yeah, of course it matters. So we need to be able to think about reliable systems. Now, there's a whole bunch of companies that make their money off of computer system reliability. They sell you highly reliable systems. And people start saying, well, here's my data. Do I really need a highly reliable system? And you look at your users, you look at your application, you look at your company life, and you say, yeah, I think I do. Or no, I don't think I want to take that, you know, spend that much money. I'll take the chances. Bichet olmaz. Yes?
This separation into sectors increase the reliability or
No.
increase performance, decrease reliability?
Listen, one more time. The fundamental message that I want everybody to get, even if you don't get anything else today, is this. If I have 1 disk and I make a big one, its failure rate is P. If I have 4 disks, its failure rate is 4P. If I have 5 disks, its failure rate is 5P. This is going to have failures more often than 1 disk. So you made it worse, didn't you, Hoja? Yes, I did. I made the reliability worse. But if I use some of these to provide redundancy, then I will not lose my system availability with a single disk failure. With this, it's going to take 2 disk failures. Well, what's the probability of 2 disk failures? 1 over P squared. Whoa, that's a big difference, because P typically is on the order of, 10 to the minus, you pick a number, 6, 7, 8. So now I square that. Oh my goodness, suddenly I've got enormous reliability. If I can take you back just a few slides, I want you to look at this. What's our goal here? Our goal here is to have a mean time to failure of disks in tens of years. In other words, my average disk failure or system failure is now 1 in 50 years. What does that mean? That means if you're Google, you don't lose your ability to support your web page except once in 50 years from these kind of hardware failures. Yeah, I could live with that. Once in 50 years, that's okay. Once in a year, too much. Once in a month, way too much. Okay? Turkish Central Bank, how often do you think they would like to have a system failure? Not very often. Do you understand? I'm trying to get across the motivation of reliable systems. Everything is not a stupid little PC. Oh, well, it failed, too bad. 500 lira PCs are not what we're going to be using when we're talking about this. This is obviously for serious servers and serious applications. Most of us are just goofing around. If somebody took my entire hard drive and threw it in, Goldbasha, I wouldn't cry too bad. There's nothing that's going to kill me. I lost some pictures, I lost some games, I lost some files I made. It's not the end of my life. But if there's some hard drives within a mile of here, if you threw them in Goldbasha, people would pull out guns and start shooting. There'd be davas, there'd be all kind of trouble. Because You know, serious money is involved in what's stored on that data. Do I understand? Multiple dimensional. This is the level that we're different. Right now, we're just amateurs. As soon as you graduate and put on a tie and go out into your first job, you move into a different world where reliability and the data matter. And people will tell you, that disk has got our entire company's value on it. For heaven's sakes, protect it. Whoa. And if you don't, bad things are going to happen to you and your family and, you know, your kids and everything else. I don't know if they'll say that, but I mean, it's serious consequences. Serious consequences. Come on now. Okay, so let's keep moving. So we want reliability in tens of years, not tens of months. That's the point. We want it to get a whole lot better. Let's get up now. Level 4 uses block interleaved parity. Before we had bit interleaved parity. Now what we're simply going to do is over here we're going to have blocks of parity that check blocks here. So now instead of distributing every bit, we'll distribute blocks. So the first block of a file goes here, the next block goes here, the next block goes here, the next block goes here, into these different sectors. And this parity block will contain the check of those blocks. All right, why would we do that? Is it any different? Still has one extra, still gets 4 times the throughput, blah, blah, blah. It allows something new. It allows us to do small reads and small writes. The last one required everybody to be involved in every read and everybody to be involved in every write. Now we're going to allow, by simply writing to this sector and changing the parity, or reading from, or you know, small reads and small writes will be not involve all members. Okay, we're going to watch which bits change when we do a write to new information, and need only to change the corresponding bits on the parity disk. So it's called read, modify, write. You read, you change, you put back. And so therefore, the parity disk has to be updated on every write, but the others don't have to be. Still gives us the limited disk failure tolerating 1. So watch this. In the level 3, we had this. If I want to put a new thing on D1, then I have to also read D2 and D3 and D4 and combine those to create the parity. So look what happened. I wrote to D1, I wrote to the parity disk, and I had to read D2, D3, and D4. Everybody was involved in a simple write to D1. This one was involved, this one was involved, this one was involved. Why? Because it was needed to generate the new parity. So you can imagine that all disks are involved all the time in RAID level 3. But now watch RAID level 4. RAID level 4 has got a really nice feature to it. We call them small reads and small writes. If I want to write something to disk 1, I write it. And I read disk 1 before I write it. And that tells me what I changed. So I know the old data, and I write the new data. Knowing what the old data was and the new data tells me what the parity change is going to need to be. So I read the old parity, and I now know what I need to write for new parity. And I didn't have to bother disk 2, disk 3, or disk 4. Wow. Okay. So now I'm going to be able to do small isolated reads without bothering the other disks. Okay. 2 reads and 2 writes, and a lot of them that aren't even touched. Every write will be 2 reads and 2 writes. In fact, that'll always be static. No matter how big this is, it involves everybody. No matter how big this is, it involves 2. The one you're writing to and the parity disk are the only ones involved. Now, that leads us to the fact that we don't have to put all the parity on one disk. We could distribute the parity. Remember, they're blocks now. I could distribute the parity blocks. I don't have to have data block, data block, data block, data block, parity, data block, data block, data block, data block, parity. I could take the parity bits, or parity blocks, and put them, distribute them. And so I'd have something like this. This is RAID 4, just what I just said. All the datas and all the parities. That means that you're always using the parity disk for every write. And therefore, if you're doing multiple writes, you're going to bottleneck here. But in RAID level 5, look what's been done. The 5th disk is just like all the other disks. It has some parity and it has some data. All of them have some parity and some data. Can you see that? So now when I look across, where's the parity? It's on this disk. Where's the parity? It's on this disk. Where's the parity? It's on this disk. Do you see what that would allow me to do? It would allow me to do parallel small reads or parallel small writes at the same time. I could do multiple reads and writes at the same time now. Watch this. Okay? If I want to write to 6, it's going to involve this parity block. And if I want to write to 9, it's going to involve this parity block. And I can't do 2 writes here at the same time because it's the same disk. But over here, if I want to write to 6 and write to 9, it involves this parity block and this parity block. So look what happens. These 2 disks are active doing this write, and these 2 disks are active doing that write at the same time. I can have full concurrency or parallelism of my writes in RAID level 5. So small reads and small writes, instead of being serialized, are now parallelized. Okay, so let's go back. RAID level 3 doesn't even allow small reads and small writes. Everybody's involved in everything. Hep, bear, bear, right? And we're all in a team. That's kind of going to wear out the disks faster and cause you to have to back up all your writes and all your reads. RAID level 4 says, don't bother everybody. So now these guys get a little rest. Their lifetime's going to be longer because you're not stressing them so much. But this one you're always using. You have a bottleneck here for performance and reliability. If you take these parity blocks and spread them out, as you've done here, now everybody's equal. We get equal loading. We get the possibility of small writes and small reads in parallel. And it works better. Okay, so that's RAID level 5. Let's summarize the RAID levels. We started with level 0. Level 1, we combined 0 plus 1 together in a special system. Level 2, level 3, level 4, finally level 5. We've looked at 7 different RAID alternatives here, and there's actually a little bit more that the book talks about, but I'm going to wrap it up. Okay, there's 4 components of disk access. We started today's lecture by talking about the seek time, the rotational latency, the transfer time, and the controller time. Those are the 4 characteristics. Typically, this is less than tenths of a millisecond. Transfer time depends on transfer rate, which depends on the spinning rate, but it's typically in this range. Rotational latency, you might as well remember these. 5.6 if you got a slow one, 2.0 if you got a high-speed fast one. But it can be calculated. Seek time, the advertised rate is somewhere in this range, but your actual rate will be lower in real systems. That's the first and most important thing that we talked about today, how do real disks behave. The second thing that we talked about was how to improve their availability by using redundancy. We took a bunch of different options, okay? Now let's summarize. RAID 1 and RAID 5, if you can remember back what those were, 5 is the last one I showed you. RAID 1 is the one where you just mirror completely. Those are really popular. It's estimated that 80% of servers have their disks in RAIDs, or 80% of the disks in servers are RAIDs. If you've got a server, you've probably got RAIDs on your disks. Why would you do that? Think about it for just a quick minute. What do servers do? They say, Buren world, give me your requests. I will serve it. So here they come. All over the web, the requests are coming. What's my goal? To get them served. So what am I doing? A lot of parallel data handling. And so therefore, my transfer bandwidth to get the stuff off the disk that the requests want needs to be fast, doesn't it? Will we always have a cache hit? No. Be nice if they always ask for the same thing. I've just got it in cache, but what if they don't? I have to get it off the disk and give it to them. So to get my high service rate from the computer and the network connection, everything I paid for, I don't want to have a bottleneck on my disks. So it makes sense to go to RAID in order to get the advantage in speed. Okay? RAID 0 plus 1. Okay? That does both mirroring and striping. And high reliability like EMC, HP Tandem, and IBM systems use 0 plus 1. Yeah, it's expensive. Okay, RAID 3, a company named Storage Concepts. RAID 4, a company named Network Appliances, uses those. Those are very special high reliability computer companies that sell you at a nice price very low probability failure rate systems. But look what the popular ones are. RAID 1 and RAID 5. Those are widely used. Nothing real fancy about either of those, okay? But all of them have a place. There's been different manufacturers that have said, I think that's the one for us. I think we'll sell our products using that. I think we'll push that. Did you know that right now in Turkey, there are companies that just can't find engineers that are interested in storage systems, want to learn about this, and yet there's a huge market for it right now. I have people that call me and they say, you got any engineers that know about disks and want to sell storage systems? I need competent people that are good with customers, that are both soft skill competent and also hard skill competent. I say, unfortunately, Most of our graduates just want to write programs. But there's nicely paying jobs right now if you'd like to work for some of these companies marketing their RAID and other storage systems in Turkey. It's called storage technology, storage systems. Okay, they deal with large backups, including tape and disk farms and disk reliability and so on. Performance matters, price matters, volume matters, application matters. You got to be an engineer to do that. And I have to tell them year after year, no, I don't know anybody. No, I don't know anybody. Would you possibly be the one? Those are some great jobs, and they're paying well, and they're looking for people, and they can't find the good people they want. Sad. So what's happening when you can't find the good people you want? Your company doesn't move ahead, your products don't move ahead, and ultimately your country doesn't move ahead. When you think about it, if Turkish companies and governments can't get the good stuff, unless some foreigner comes all the way here and markets it because they're willing to, then probably those products just won't be sold. It'll be very hard to get or get the support you need. Okay. Now, RAIDs have enough redundancy to allow continuous operation. Even when a failure, you can keep running. But that means that you have to do what's called hot swapping. While your system's running, you've got a failure. You've got to get the failure out and get the replacement in. That's called hot swapping. It's literally taking something out and putting something in without disturbing the operation. If you say, oh, we've had a disk failure, we've got to shut down for an hour, there's a lot of managers that will say, what? We're not shutting down for 1 minute. Never mind 1 hour. We got to stay up. This is a bank. This is a web server. This is a whatever. I mean, you don't shut down. So hot swapping is a real important thing to do. We didn't really talk about it, but the ability to get a new disk in while the disk system, the RAID system is running, is non-trivial. Replacement while running is a very challenging problem. So again, there's a number of issues to be looked at here. All we've had time to do is kind of skim the surface. And that's the end of our surface skimming. So have a good afternoon, you guys. I'll see some of you this afternoon after class. I'll see some of you all tomorrow morning in my office for appointments. Let's do this oral design review and move on to the next phase. Okay. Görüşürüz. Hoşça kal.